This is an AQA A-level chemistry year 12 topic. It's amount of substance. This is part one, where we are going to be looking at using the periodic table and some basic mole calculations. As always, I'm going to recommend that you try each task, pausing the video as you go, and then review your answers. And that way you get to know what you know and know what you don't know. So let's get straight onto it. We have got the learning objectives here in terms of atomic mass, molecular mass, Avogadro and the mole. And there's a question down at the bottom here that is often discussed about why carbon might be a better standard than hydrogen. Now what we're looking at here is that carbon is stable, easily available, and it has an exact mass of 12, carbon 12, 6 protons and 6 neutrons. And that makes it a very suitable standard. Now we're going to move on, and we have got some of the key definitions here. Not a lot to do here apart from read them, learn them and understand them. But the question at the bottom is an important one, because we've got relative atomic mass and relative molecular mass. Why might we use the term relative formula mass, specifically in the case of an ionic compound? So the key reason is that when we talk about sodium chloride, as an example, NaCl, there's an implication there that maybe it means one sodium ion with one chloride ion. But we know that's not the case. We know that these are giant lattices. So the formula mass gives the ratio of the number of sodiums compared to chlorines. It doesn't imply that there's only one of each. So this next task is really thinking about using the periodic table. And I want to take a look and try and work out what has been done wrong in the questions on the right hand side. So if we take a look, a student said the relative atomic mass of lithium is 3. What have they done wrong? Well, hopefully what you're seeing here is that lithium has got an atomic number of 3, but it has a mass number of 7. So actually, when we talk about the relative atomic mass, they should have used the mass number of 7. Then we've got a student who said the atomic mass of magnesium was 24. What have they done wrong? Well, in a sense, you could argue here that what they've done wrong is use the old GCSE periodic table, or they've memorised a number and not got the specific detail. Because magnesium isn't 24 when we discussed this at A level, it's 24.3. And finally, a student said the atomic mass of sodium was 23. What have they done wrong? Well, if you go to the periodic table, sodium does have a mass number of 23. But that won't get you the mark at A level, because whenever we talk about relative atomic masses, you must include one decimal place. So you would have to write down not 23, but 23.0. We've got some examples for you to try here. Pause it, make sure that you're getting the right numbers, or that you can get to the right numbers, and then we can review once you unpause. So you can see that I've included the one decimal place in each case. I've taken them directly from the periodic table. I haven't learned these. I am very much using information that has been provided. Remember, always include the one decimal place. Moving on, finding the relative molecular or formula mass of a substance. And we have got here 3 examples of molecules that aren't compounds. Now, I've not written this in actually, but it is a very important question. You can have molecules that are not compounds. Think about all of the diatomic molecules, the diatomic elements, hydrogen, nitrogen, oxygen, and then all of the halogens. They're definitely molecular, they're in pairs, but it's one type of atom, so they're not compounds. But the key bit as we go through here is to look at the word examples and then work out the relative molecular masses. So pause and see how you do. So for HCl, we know that hydrogen is 1, chlorine is 35.5, so that comes to 36.5. You can see it's to one decimal place. Oxygen Each oxygen has a mass number of 16, so we have 2 of those. Remember, we need that decimal place, 32.0. And following that same procedure through, with sodium being 23, oxygen 16, and hydrogen 1, that takes us to a value of 40.0. 3 more for you to pause and try here. So moving into slightly bigger numbers, potassium bromide 39.1 and 79.9 gives us 119.0. H2SO4, so we've got here 2 hydrogens, a sulfur and 4 oxygens. Add all of those together, we get 98.1. And finally, sodium tetrahydridoborate, NaBH4, 1 sodium, 1 boron, 4 hydrogens, and it comes to 38.0. Remember, I know I'm repeating myself here, you don't include the decimal place, you lose the mark. And then 3 more examples to pause and try. Slightly more complicated again, not difficult maths, but fiddly maths, a lot more numbers to play with. So potassium dichromate, 2 potassiums, 2 chromiums and 7 oxygens, comes to 264.2. We're dealing with brackets here. Remember, the 2 after the brackets means 2 NO3s. That's 2 N's and 6 O's. Add all of those together, 148.3. And finally, aluminium sulfate with its 3 SO4s, 2 aluminiums, and that comes to 342.3. Moving on now to using Avogadros number. Taking a look now at using Avogadros number, we've got a definition here, and there are some questions at the bottom on the left-hand side that, once you've read through what's above it, will maybe seem like slightly odd questions, but there's a really important reason that I'm asking them. So have a think. And now let's take a look. How many eggs are there in a dozen eggs? Well, there's 12. In a baker's dozen, that's something you might be familiar with, maybe less familiar, but that would be 13 loaves. And how many days in a fortnight? We know that it's 14. The reason that I'm reinforcing those points is that Avogadros number is just a name given to a number. The actual number in this case is 6.022 by 10 to the power of 23. That's going to be provided for you. But you have to understand that that's what Avogadros number is, and then it's about applying that knowledge and using it. We've also got at the top, actually, normal to focus on moles rather than individual atoms. Why is this the case? Well, that's because they are very small. We want to work with manageable numbers. Got the numbers there that we discussed. And now, taking a look on the right-hand side here, it's trying to find the links between number of moles, Avogadros number, and atomic molecular or formula mass. So all I've done here is just piece together, we know that 1 mole of lithium hydroxide contains 6.022 by 10 to the power of 23 molecules of LiOH. And we also know that 1 mole has a mass in grams equal to the relative molecular mass. Now, lithium hydroxide is 24 grams because it has a relative molecular mass of 24.0. So we also then know that 24 grams is the mass of 6.022 by 10 to the power of 23 molecules of LiOH. So we can find the mass of 1 molecule by dividing that 24 grams by Avogadros number. And that's a little 1 marker that does commonly come up. I'm just highlighting here something that's really important, and it's about being able to talk with certainty about figures. So 10 moles of hydrogen doesn't tell us much. Do we mean 10 moles of H2 molecules, or do we mean 10 moles of hydrogen atoms? That clarity is absolutely vital. Moving on, we're going to look at some calculations now, and we have got here some important calculations, some important equations. You need to be able to use them, apply them, and rearrange them. Now I'm going to put it into a triangle. I'm also going to add a second triangle for a calculation that's going to follow later on. But if we know that number of moles is mass divided by molecular or atomic mass, we can do some rearrangements and conversions. I've also included moles is concentration times volume. Now if I add in some little symbols, I can see that MR or AR is mass divided by number of moles. I can see that volume is moles divided by concentration. It's really important that you are familiar with these equations, that you can rearrange them, and that you can use them effectively. And we're going to look at some examples of that. So we've got worked example on the left, and then a chance for you to do the calculations on the right hand side. Pause, give them a go, and then we can review. So in the case of how many moles are there in 190 grams of sodium tetrahydroborate, well, we've got 190 as our mass. We've got our MR is 38 when you add those together. So we get 5 moles of NaBH4. If we're looking at how many moles there are in 7.2 grams of LaOH, mass has been provided. Divide that by the MR, 24, we've got 0.3 moles. If I want to calculate mass, remember we're rearranging that equation, potentially using the triangle if you need to. What's the mass of 0.2 moles of calcium hydroxide? Well, in this case, we've got moles multiplied by MR, 0.2 times 74.1 takes us to 14.82 grams. And what's the mass of 0.6 moles of NaCl? Well, again, moles multiplied by MR, that's 0.6 multiplied by the 58.5. That comes from 35.5 chlorine, 23 for sodium. We get 35.1 grams. And if we want to calculate MR, well, in this case, we want the MR of a substance if 3 moles have a mass of 96 grams. Well, MR is moles divided by mass. 96 over 3, that takes us to 32. And if I've got 352 grams and 8 moles, 352 divided by 8 gives us an MR of 44. However, for the calculation, we have not yet got the marks. Because we're answering the question with an MR, it needs to be 32.0 and 44.0. Carrying on here, we're calculating moles in solution. I've already shown you the triangle, but N is C times V. Moles is concentration times volume. Worked example provided. We've then got some for you to try. Pause and give it a go. So in this case, we've been given a mass. We actually need to work out the number of moles. We're using N is M over MR. 10 divided by 40 means there are 0.25 moles in 1,000 centimetres cubed. Now actually, we're converting that cm cubed into dm cubed. 0.25 divided by 1 means that we have got a concentration of 0.25 moles per decimetre cubed. It's really important, because concentration is in moles per decimetre cubed, that the volume is in decimetres cubed. On the next one, 19 grams of MgCl2. So we do 19 divided by 95.3, the MR, and that takes us to 0.2 moles. Now in this case, it's in 750 centimetres cubed of water. We convert that to 0.75 decimetres cubed, taking us to a value of 0.27 moles per decimetre cubed. Got some more examples here for you to try. Pause, see how you do. 25 gram sample of NaCl, so that's 25 divided by the MR, 58.5, we get 0.427 moles. We've got a concentration of 0.2 here, so we need to know the volume. Now, because my concentration is in moles per decimetre cubed, my volume is going to come out as dm cubed, 2.13. You could convert that to 130 centimetres cubed. And then we move on to the final question, 6.5 grams of KBr. So 6.5 divided by 119 tells us it's 0.0546 moles. It's in 200 cm cubed, which we convert to 0.2 decimetres cubed, and we get a concentration of 0.273 mole dm to the minus 3. So we've got the basic introduction to molar calculations. We've got some of the key information about relative molecular masses, where to find them, how to write them. In part 2 of this walkthrough for this topic, we're going to take a look at the ideal gas equation. Thank you for listening. Goodbye.